What I want to do in this video is give ourselves some practice and hopefully some intuition on multiplying a scalar times a vector. Now, what am I talking about when I say multiplying a scalar times a vector? Well, let me set up a little two-dimensional vector here. So let's say I have the vector w, and let me give it an x component. Let's say its x component is 1, and its y component is, let's say it's 2. And I could draw it if I like. Actually, that's a good idea. It's always nice to be able to visualize these things. Let me get some coordinate, get a coordinate axis here. So that's my x-axis. That is my y-axis. And so if I were to draw this vector in kind of standard form, I would put its initial point at the origin, and then its terminal point would be at the point 1, 2. So its x-coordinate is 1. Its y-coordinate is going to be 2. So 1, 2, this vector is going to look like, its initial point is right here. Its terminal point is going to be right over there. The vector in standard, graphing it in standard form or visualizing it in standard form would look like that. Now, of course, I could have the same vector and I could shift it around as long as I have the same length of the arrow and it's pointing in the same direction. But if, no one tells you otherwise, it's nice to just put its initial point at the origin. Now let's multiply it by a scalar. Now what do we mean by a scalar? Well, a vector is something that has a magnitude and a direction. A scalar is just something that has a magnitude. You could think of just the numbers that you started learning when you were 4 years old, that those are scalars. So for example, we can think about what is 3 times w going to be? 3 times w. 3 is a scalar, w is a vector. Now the convention we use for multiplying a scalar times a vector is you just multiply each of the components times that scalar. So this is going to be equal to, we have a 1 and a 2, and we're going to multiply each of those times the 3. 3 times 1, and then 3 times 2. And so this is going to be equal to, 3 times 1 is 3, 3 times 2 is 6. And so we see the resulting vector, 3, we could call this vector 3w, or it's going to have an x component of 3 and a y component of 6. So if I were to draw it in standard form here, x component 1, 2, 3, and then y component 2, 3, 4, 5, and 6. And so it's going to look like this. Let me see if I can draw it reasonably. It's going to look like this. And obviously I'm hand drawing it, so it's not going to be exactly right, but it's going to look like that. So this is the vector 3 times w. Now notice what happened when I multiplied it by the scalar. The direction didn't change, but the magnitude did. And you see what the magnitude changed by. It increased by a factor of 3. This was the length of my blue arrow now is 3 times the length of my magenta arrow. Let's do another example. And I'll use the same vector w since we already have it set up. Let's multiply it times a negative scalar. So let's see what happens if I multiply negative 2 times w. And like always, I encourage you to pause the video and think about what this would be. And even if you have the time, graph it out. Well, we would multiply each of our components by negative 2. So it would be equal to negative 2 times 1. It would be the x component, and then the y component would be negative 2 times 2. And so this is going to be equal to the vector negative 2, negative 4. Well, let's plot that. So the x component is negative 2, so that's negative 1, negative 2. And then the y component, negative 1, 2, 3. I'm going a little bit off of my axes. 4. So that would be negative 4 there. That's a negative 2. So it's going to look something like this. It's going to look something like that. So that right over there is the vector negative 2w. Now let's think about what just happened. Well, because we had the negative here, it essentially flipped the direction by 180 degrees. It's going in the opposite direction. But one way to think about it, they kind of would still sit on the same line. So the negative just flipped its direction. If you consider whatever direction this was, the magenta vector W was going, it's now going to go in the opposite direction. And then it also scaled it up by 2. This is twice as long, has twice the magnitude of our original vector, and it's going in the opposite direction because of the negative sign. So hopefully this gives you a little bit of intuition of what it means to scale a vector. I mean, literally the word scalar has the let me write it down. Scalar. That's a scalar. That's a scalar. It has the word scale in it. It's literally just scaling the vector. It is changing its magnitude. It might flip it around because of a negative sign, but it's essentially changing its magnitude, scaling it up or down or flipping it around with a negative sign.